Hi guys. All right, my darlings, so today we're looking at U substitution. This is one of the techniques of integration that we use, and it really helps us simplify difficult integrals, okay, so that they're easier to use. The key here is to find a piece of the integram whose derivative is also in the integrand. So if you can see part of the integrand whose derivative is also there, that original part is going to be your u, okay? The role of substitution really is to reverse the chain rule, okay? It helps us undo the chain rule. We know integration is the inverse of differentiation. So this u substitution helps us undo the chain rule, which makes the problem look more complicated. Now I'm going to give you the steps for u substitution so that you have them all typed out here to begin with. But then we're going to go through slowly and see how we use that, okay? So the procedure for u substitution, like I said before, is to look for a piece of the integrand whose derivative is also in the integrand. Now, if you're not sure what to use, which is sometimes, especially at the beginning, tough to find, try letting the denominator be the u, or if you have something really messy, like a big polynomial being raised to a power, that would be your u, okay? Remember when we used to look at the inside of functions and the outside of functions? The inside function is your u. So u is your inside function, and we're going to look at inside and outside functions again, okay? Once you know what your u is, you're going to write down what your u is. You're going to take the derivative with respect to x, or whatever variable you have. So that would be du dx. You're also going to solve that du dx for dx, so that you can, in your integral, go back and replace your u and dx with what you have chosen and solved for. You're going to plug them into the integral, and you're going to simplify. And this new integral is going to be much simpler to solve, okay? If you have an indefinite integral, which means there's no upper and lower limits, you need to convert back from the u's to your original variable. So that's important to remember. If we have numbers, we're not going to convert back. All right, so let's go through first and talk about what should be a u and what isn't a u. Now, remember the inner and outer functions, okay? Here's an example. If we have an integral of x squared times the quantity x cubed plus 1 raised to the fourth, this x cubed is on the inside. This is what we would let our u be equal to, okay? And then the outside function is, what did we do to this x cubed plus 1? We raised it to the fourth, so the outside function is x to the fourth. Okay, let's look at the next one. The integral of 2x plus 5 all over the square root of x squared plus 5x plus 1. So, remember, one of the suggestions for our inside or our u is to look at something being raised to an exponent or in the denominator. Well, we have something in the denominator that's also raised to an exponent, that x squared plus 5x plus 1, okay? Notice also the derivative of x squared plus 5x plus 1 is 2x plus 5. That's sitting in the top. Remember, we said look for something whose derivative is also there. So our inside function is x squared plus 5x plus 1. But what function did we plug that into? Well, it's in the denominator, and it's also under a square root. So that will be the function 1 over the square root of x, or x to the negative 1/2. Probably easier to take the antiderivative if we write it as x to the negative 1/2. Let's look at another one. We have the integral of dx over the square root of x times the quantity 1 plus the square root of x cubed. Now, once I say the quantity, that's usually an indication that we have an inside coming up. So our inside is 1 plus the square root of x. And what did we do to that? We cubed it, but it was also in the denominator. So that function is 1 over x cubed. Okay, two more. The integral of the quantity x cubed plus x times the quantity x to the fourth plus 2x squared plus 7 raised to the 3/4 dx. Now this is a really big messy polynomial raised to an exponent. So that inside x to the fourth plus 2x squared plus 7 is our inside. And what did we do to it? We raised it to the 3/4. Now, one thing that I forgot to mention, because if you notice, if you take this derivative, it's 4x to the third plus 4x. That's not quite this, but one of the things I forgot to mention back here, okay, is when I said we want to look for an integrand whose derivative is in the integrand, that derivative is allowed to be off by a constant coefficient because we can adjust for constants. We can adjust for a 4 so that when this 4 is missing, we'll be able to adjust for that. But we're going to do that a little later, not right away. Okay, let's look at the next one. The integral of secant squared of x over 4 dx. Whenever you have a trig function, the first thing you look at is the angle. If the angle is not a simple x, that's your inside function. It's inside the trig function. That's going to be our u when we're ready to do u substitutions. And then our outside function is secant squared of x. Okay, now we're actually ready to look at how a u substitution works. So here's an example for us already. It's the integral of x squared times x cubed plus 1 to the 4th dx. So we let the inside function x cubed plus 1 be our u. Now if we take the derivative of u with respect to x, that's du dx, and the derivative of x cubed plus 1 is 3x squared. Now, if we multiply both sides by dx, we'd have du equals 3x squared dx, and then if we divide by the 3x squared, we now have our dx equals du over 3x squared. Now we're ready to use our substitution. So we're going back to this function, okay? We have the integral of x squared. That can't change. However, our u in here is that x cubed plus 1. There's our u, and it was raised to the 4th. And the dx is this du over 3x squared. That goes in here. Now, if you look at this x squared here is going to cancel out with this x squared in the denominator. Now, the 1/3, that 3 in the bottom, that's a 1/3. It's a constant. It can factor outside the integral. And then all we have left is u to the 4th du. That's an easy antiderivative to take. We keep the 1/3. We raise the exponent to 5, raise it by 1, so it's u to the 5th, but divide by that new exponent 5, and don't forget to add your plus c. 1/3 times 1/5 is 1/15th, and now go back and replace u is x cubed plus 1, raised to the 5th, plus c, and there is our answer to this original integral, which looked really hard to do, but it wasn't that bad when we break it up. Let's try one. Now, I know yours looks like it's the chart, but I want to make sure that you can actually read everything that I'm doing clearly, so I spread my chart out. That's all that it is. Okay. So I have the integral of 2x plus 5 over the square root of x squared plus 5x plus 1, and we looked at this one before and said that the inside was x squared plus 5x plus 1. So that's my u, x squared plus 5x plus 1. Now we're going to take the derivative of that. The derivative of u is du dx equals the derivative of x squared is 2x, plus the derivative of 5x is 5, and the derivative of 1 is 0, so we don't need that. Now we're going to solve for dx. So we have du equals 2x plus 5 times dx, or du, and if I divide by the 2x plus 5, that's my dx. Now I'm ready to make the substitutions. So we have the integral of 2x plus 5 over the square root of, now this x squared plus 5x plus 1, that's my u, and this dx, that's my du over 2x plus 5. Now when I go to simplify this, my 2x plus 5s are going to eliminate each other. And we have the integral of 1 over the square root of u du. Now it might be easier to write this as u2, if it's in the denominator, it's a negative exponent, and the square root is a 1/2 exponent, du. Now to take the antiderivative, we keep the u, add 1 to the exponent, that's a positive 1/2, divide by that new exponent 1/2, which is the same as multiplying by 2, and don't forget to add a plus c. Last step. Now remember, The 1/2 is really the square root of u plus c, and now the last step is to replace that u was x squared plus 5x plus 1, and don't forget to keep your plus c. There you go. We did an integral with u substitution. Now, one thing to kind of help you remember, and I'm going to give you these models as we go through this unit, but these models are not new things to remember. They are just reminders of how to undo the derivatives. You already know the rules. They are the derivative rules in reverse. If you have u to the n, that means it was u to the add 1 to the exponent and divide by the new exponent. Don't forget your plus c, but remember, this does not work if n is -1, because if the original was u to the -1, if you add 1 to that, it's u to the 0 divided by 0. You can't do that. So this does not work when it's u to the -1 du. That's something else. Okay? So anytime you have something raised to a power, you're going to let that inside be the u. Okay? So we're going to determine u, the inside. So u is going to be the x plus 2. Now we're going to take the derivative of that. So du dx is the derivative of x plus 2 is just 1. So if I multiply both sides by dx, I know that dx is just du. Now we have the integral of x plus 2 is my u. It was raised to the 5th, and my dx is just du. I can do that antiderivative. We add 1 to the exponent, we divide by our new exponent, and add c. Last step, go back. What was u? u was x plus 2. Don't forget to raise it to the 6th over 6 plus c. And by the way, yes, it's okay if you write it that way. It's also okay if you write 1/6 times x plus 2 to the 6th. Plus c. Either way, they are equivalent, does not matter to me. Okay, so far so good. All right, guys, now the next one. This model 2 is a reminder of your trig derivatives. Remember, if we had sine of an angle, the derivative was cosine u, so the integral of cosine is sine u. The integral of secant squared u, what has a derivative of secant squared u? It's tan u plus c. What has a derivative of secant u tan u? That's secant u plus c. The ones you have to be careful of, as always, are the cofunctions. The antiderivative of sine u is negative cosine, because remember, the derivative of cosine x was negative sine x. So therefore, the antiderivative of sine u is negative cosine u plus c. Okay, so these are all the same rules you already know. Do not panic. You know them already, or at least you're supposed to know them already. So again, when we're going to do a u substitution and we have a trig function, 9 times out of 10, the u is the angle, 7x plus 5, because it's inside the trig function. So now we know what u is. Now we're going to take the derivative, du dx, and the derivative of 7x plus 5 is 7. So if we multiply both sides by dx, and then we divide by 7, we now know that dx is du over 7. So I'm going to go back to this integral of the cosine of, but my 7x plus 5 is just u, and my dx is du over 7. So now that 7 is a constant. I can factor out 1/7 and say, okay, if the cosine of u du, that's 1/7 times what has a derivative of cosine? That's the sine of the angle u plus c. One last step, I keep my 1/7 times the sine of, wait a minute, what's my u? 7x plus 5, and then plus c. We have now evaluated the integral. All right, guys, so this is the introduction to the beginning of u substitutions to help us simplify some of our integrals. We will definitely be doing more of this. Have a great day.